Thanks a lot for the introduction. So I want to start with some very basic intro into what we want to achieve in Terahertz Spintronics. So as we saw in the first talk yesterday, there are certain operations we want to achieve at terahertz frequencies. One of them is to turn spins around. The second one is to transport spins through space. And the third one is to detect spin dynamics. And in this talk, I want to focus mainly on the first part, on how to turn spins around. And specifically, I want to focus on torques. So if you look at the very simple equation, so half of the Landau-Lifshitz equation, you could say, then you can see that the rate of change of spin angular momentum is proportional to an effective magnetic field that this spin sees, or that is applied to this spin. So contributions to that spin can, of course, be applied magnetic fields that you have with an external magnet. You can have spin orbit fields, which in turn may lead to magnetocrystalline anisotropy. And then there, of course, will be exchange fields. If you look at typical strengths of these fields, then the first two will be around 1 Tesla. There might be some cases where they are higher. But if you look at the exchange fields, they can be much larger, about 100 or 1,000 times larger than that. So if you look back at this equation here, you can immediately see that the frequency or the rate of change will be much faster if you can somehow use exchange fields. And you might also get stronger amplitudes. So a natural question would be, can we exploit these exchange fields to get fast dynamics? So in a typical ferromagnet, here I plot one, if the spins are parallel, there will be no exchange torques present. And this is also the case for antiferromagnets, where you will have antiparallel spins, but still no torques, from exchange at least. What happens when you cant the spins is that then you can get exchange torques. They will drive the spins into opposite directions, and this is exactly this exchange that you would be interested in. But you've just shifted the question now in how to cant spins in the first place. And of course, there are various solutions to that, but in certain antiferromagnets, there is one possibility that I want to look into, and these are the so-called Néel spin orbit torques. So what are those? They have been proposed some years ago in metallic antiferromagnets, such as manganese to gold and copper manganese arsenide. And what these two have in common is that they have collinear sublattices, A and B. And by the way, I defined the Néel vector as just the difference between the sublattices. And now what happens in these materials is when you apply an electric field, then you will get an effective spin orbit field on the sublattice. What's special now here is that they have locally broken inversion symmetry, these materials. So on the sublattices, the effective spin orbit field will change sign. So you will have opposite spin orbit fields on these sublattices. And this in turn gives you a torque in the same direction, and this is the spin canting. And this could give you the exchange enhanced dynamics. So our question was whether we can use these Néel spin orbit torques to see terahertz magnons, exchange enhanced, and ultimately whether one could use such magnons to then switch a bit, possibly coherently. Okay, to answer these questions, we need some ultra-fast experiment, and I want to show you how our experiment looks like. So we have a thin film of manganese to gold on a sapphire substrate. It was prepared by Martin Jordan's group in Mainz. And now we come with an intense terahertz pump pulse. And of course, this pump pulse will have two fields inside, or composing it. So you will have an electric field and a magnetic field. And in our geometry, we can flip the field of this pump pulse to see which dynamics are triggered. We probe the dynamics then by an optical probe pulse, which traverses through the sample, and we detect the polarization change after traversing. So which samples specifically do we look at? So we have two types. The first is as grown, so as it is made in the sputtering chamber. And there you will have basically 90-degree domains which are equally populated. So overall, there will be no net orientation of your magnetic order. You can also place these samples in a very strong magnetic field of 60 Tesla, and then most of the domains will align perpendicular to the magnetic field. Sometimes you hear this referred to as a spin flow. And this can give you some local magnetic ordering. And if we have such a local magnetic order, we can actually rotate it by just rotating the sample. Okay, so let's look at some signals that we got for these pre-aligned samples. So here I plot the time between the pump and the probe pulse, and here's the signal. And the signal that we get is something that is definitely bipolar, so it has positive and negative amplitudes. And what is interesting about it is that when you compare it to the terahertz electric field that is impinging on the sample, our signals look much different. So they are slower, meaning there's some internal dynamics that we are here probing. We can now ask what happens when we change the field polarity. And actually we see that our signal mainly changes sign. So there's a strong component which is odd in the terahertz field. And we can extract that by just taking the difference between these two curves. This looks like this then, but now we could ask what happens when we rotate the sample. So we rotate it around the probe position. So if you rotate the sample by 180 degrees, you also see that the sample or the signal changes sign. And this indicates that there seems to be some kind of arrow that you can rotate by azimuthally rotating the sample. And one question we posed then, of course, could this arrow be then the Néel vector, so the staggered magnetization here? For that, we compare different samples. So the pre-aligned sample I've already shown you. Now, it could be something very simple that we just observe some kind of effect from the substrate. So we check the bare substrate of sapphire, and we see no signal in terms of what you can resolve in our experiment. If you look at the S-grown sample, where there is no defined direction of a Néel vector, you can also get very small signals only. So we deduce that this built-in arrow that we've been rotating is actually the Néel vector inside the sample. This gives us two things to work with now. We have a signal that is odd in the or in some kind of field of the terahertz pulse, and is also odd in the Néel vector. But now we can ask, which field is it? Is it the electric field or the magnetic field of the terahertz pulse? For that, we went into a symmetry analysis. And if you do space inversion on this material system, plus the driving fields, then you can see that the Néel vector and the electric field will change sign, whereas the magnetic field does not. And this links the first two together. So if you have a signal that is proportional to the electric field, it must also be proportional to the Néel vector. This is the simplest case. It does not only hold in the linear case, but in general for all odd higher orders of such effects. We did also some additional symmetry analysis, which I'm not going to show, but it involves the probe polarization dependence as well. And what this tells you is that the signal that we've measured here is proportional to delta phi. What is delta phi? It is actually the in-plane rotation of the Néel vector. So we see that oscillation in the signal that I show here. So how can we model this? For that, we go back to the simple case where we have the two sublattices being anti-parallelly aligned. And now let's look at the very simple case, an electric field which is just a delta-like impulse, so very short. There will be Néel-Swinobit torques canting the magnetizations out of the sample plane, but now there's the spin canting, so the exchange torques will become active, and they drive the spins in opposite directions. So if we look from the top now, we can see that the Néel vector actually rotates because of this. But this orientation is no longer, let's say, a minimum of the anisotropy potential. So there will also be anisotropy torques acting on it now. They will push the sublattice magnetizations down, and you get a precession. This precession we expect here is mostly in plane because the exchange fields are strong, the anisotropy fields are much weaker. And of course, it is exchange enhanced, so we have the strong field acting here, we expect fast dynamics. So if I were to solve the underlying equations here, I would say that the Néel vector angle behaves, well, causally. You have a heaviside function here, so nothing happens before you excite it with your pulse. and then you will have a sinusoidal damped oscillation. Why is it sinusoidal? Well, you first have to build up this canting, and then you get a deflection of the Néel vector. So let's see whether this fits our data. So we go back here. This is our data, the blue curve, and the black curve is the electric field. You can immediately see it is not a delta-like impulse. So this might look like a problem, but actually in the linear regime, it's very simple to just use a convolution of the electric field with some basic response function. And we can try to fit this now to our data, and actually you see that the fit captures the dynamics very well. And this allows us to get fully rid of the electric field that drives the process and just get the response function. And that is again the sinusoidal oscillation that we have seen. And you can see that the frequency that we measure is 0.6 terahertz. So this is the bare frequency without the damping. And this is intimately related to another property of this sample, the so-called spin-flop field. And so we can use our frequency to calculate what the spin-flop field should be, and we get 20 Tesla. And this is in nice agreement with some previous measurements directly looking at spin-flop fields. What you can also see is that even though the frequency is 0.6 terahertz, the damping is very strong here. And this can be understood in terms of another exchange enhancement here. Since the Gilbert damping is on the order of 10 to the minus 2, so not exceptionally large, but since there's again exchange happening here, this may be going up as well. Okay, so this Gilbert damping is consistent with other metallic antiferromagnets we have looked at. There are not so many values in the literature, but some are agreeing quite nicely. So we have a strongly damped terahertz magnon. Now, we would like to ask another question here, or two questions actually, which I haven't answered. What is the strength now? So we have the electric field driving some spin oscillation, but what is the effective spin orbit field that we get? How strong is this coupling here? And then related to that, how strong is the deflection in the plane? Are we talking 1 degree or more? The calibration of this is quite difficult in the linear regime because you're lacking some essential prefactors to your signals. But we found that the nonlinear response can give us some very nice insights into that. So let me explain to you how this could work. So if you look at the anisotropy potential for the Néel vector angle in the plane, what we've done so far is we have assumed it's a linear system, and that means we have a harmonic potential. So an oscillation will just follow this parabola here. In truth, however, the anisotropy potential of this system is actually of cosine-like dependence, so it will drop off here, and actually if I would plot this further, it would go down again to give you 0 and 90-degree minima of this anisotropy potential. Now, if you were to drive with, again, just a delta-like impulse, some dynamics in the system at different strength of the impulse, you will see something, well, perhaps it's expected, but maybe also a bit surprising. So if you kick this system, you can see that this one, the purple one with the strongest excitation, actually lags behind considerably behind the others because it just takes longer to get down from here. You can also plot this over time. So here's now the angle over time, and you can see these waveforms look strongly different, and the shape of the waveform is directly related to the strength of the excitation. And that, even without some prefactors, gives us a way to calibrate our amplitudes here. But what you would need, of course, is that we actually reach some nonlinear regime. So we wanted to see whether this happens in our signals. So here I plot the signals divided by the driving field strength. That just makes things a bit easier to see. And this red curve here is the signal that we've been looking at, which is definitely in the linear regime. We also checked that. Now we increase the electric field that we use to drive. What we would expect is, if it's still linear, the waveform will not change. So it will be the same strength, and it will just look exactly like the one before. And what we measure is actually also that. So you can see that there is no strong change in the waveform, meaning this is still in the linear regime. Let's drive the system with an even stronger field. Again, this is what we would expect. But now the waveform we measure looks like this. So you can see that the waveform strongly changes upon reaching this field. So there's some nonlinear dynamics. We can try to model those with the anisotropy potential I showed you before, also taking into account the probing. And then we can try to fit these curves with single set of parameters. And the black curves, I hope they show up here, nicely capture the dynamics we measure. So this allows us to extract an effective spin-orbit field. So I've been wondering on how to phrase it here. Basically, if you drive a current through this metallic antiferromagnet, for every 10 to 11th amps per meter squared, you get 8 millitesla of effective spin-orbit field. And this was a bit higher than what was calculated in DFT some years ago. So we think it's quite reasonable. Secondly, we can now look at the deflection that we get at the strongest field excitation. And that actually reaches up to 30 degrees. So to put this into perspective, I plot here again the anisotropy potential. And you can see that 30 degrees would actually be going up here. So you reach close to the potential barrier of the system. Okay, we couldn't go further in experiment, but we can extrapolate in theory what will happen and simulate it. So that's what we did here. We can see that these are the first two excitation strengths I showed you. If we go a little stronger, this is where we ended up in the experiment. We get up to here, but now let's extrapolate. So you can see that the signal becomes more and more nonlinear the further we go, actually reaching some kind of unipolar shape here. And if we go a little bit higher, then in a coherent way, we would switch or rotate to a different position here. The end position would then be 90-degree rotated spins. And this switching time that you can see here is on the order of 1 picosecond, so you really take advantage of the strong exchange fields. This is also somewhat stable, so you can increase, okay, this didn't go as planned. You can increase the electric field a little bit and you still end up at 90 degrees. But if you go further than that, you can actually rotate over this first minimum and end up in the next one, which is at 180 degrees. So it seems to be possible to switch by 90-degree steps in this material with strongly applied or strong electric fields. And the one here basically corresponds to 40 kilovolts per centimeter inside the sample. So exactly, so might be reachable in further experiments. Before I sum up, I would like to thank the people at the Terahertz Physics Group at Freie Universität Berlin, especially Alex Chekhov and Oliver Gückstock for doing many of the experiments with me. And they also have posters, so make sure to check them out. Then, of course, our collaborators in Mainz for growing these samples, and Helen for the theory. And then also special thanks to Juris Kurski at Helmholtz-Zentrum, because he placed the samples in these strong magnetic fields to pre-align. With that, I would like to summarize that we see signatures of the Néel spin orbit torques. So this means driven by electric fields, we get some coupling to the spins. And we observe a terahertz magnon, which is exchange enhanced. And I just made a small cartoon here, how the oscillation of the sublattice looks at the moment. And we can reach up to 30 degrees of deflection in the plane. Now, if we could go to 2 or 3 times higher terahertz fields, it would look like this, and we would go from 0 degrees to 90 degrees in about 1 picosecond. So, from an experimental point of view, of course, there are some questions still open. And first of all, if we want to see some coherent switching, we somehow need to be sensitive to these opposite domains, so these 90-degree domains. We also need to make sure, if we want to do a pump-probe experiment, to bring the sample always back to the initial state. And of course, most importantly, we need to increase or enhance the electric field inside the film to actually get to this stage here. And we're working on all three of these things, so I'll be happy to discuss them as well if you like. But with this, I want to thank you for your attention. And
thank you very much.